So in this little clip I'm going to do what we planned to do last Thursday in the MATLAB class, but didn't work because the stats licenses were all checked out. So just go to some folder. Yeah, I created folder, MATLAB work folder for my econometric methods course. I uploaded a new version of the OLSS.m code. It's here. You can either copy and paste, or you can just download from this link from the Eclair web page. So I'll do that. I'll just need to find the right folder and MATLAB here. Okay, so I'll save OLSS.m in the folder in which I'm gonna work. Then I have a new script file. I called it FirstSteps.m. So in here I want to create series which we're gonna feed into a regression, and we said that we're gonna create random numbers. So firstly I define how long my series should be. I'll actually let it be 1,000 observations. You could choose whatever you want. So I create a variable called t, capital T, which has a value of 1,000. Then I want to create my dependent variable. So what I want here is, let me write a comment first, a 1000 by 1 vector of random numbers. And let's say I want uniformly distributed random numbers. So that's uniformly distributed on the interval between 0 and 1. The command for MATLAB to use that is quite intuitive. It's just called rand for random numbers, and then you need to tell MATLAB how many rows and how many columns you want. Now rows, we want capital T rows, 1000. So however long we defined T to be, we want that in here, and we only want one column. So this is now our Y. We said we also want to generate an X, and what I'm gonna first write down what I do, and then I'll explain it. 1. So it's almost the same. I call a random number generator again, but now the command is rand n, just because I want to introduce that, and this is now 1000, or better a t by 1 vector of random numbers, but this time not uniformly but standard normally distributed, so with 0 mean and variance 1. Okay, and that little n after the d makes the difference. The command rand creates uniformly distributed random numbers, rand n creates normally distributed random numbers. So now we basically want to feed this data into our OLS routine. If you don't quite remember what OLSS requires, just type help OLSS, and on the screen you get the description. Basically you can copy this. Actually, before I do that, I want to call these my Y and my X. You can give them, these guys, whatever name you want. Okay, and then here you can see the shape of the function which you need to call. So OLSS, here are the inputs and here are the outputs. Let's take care of the inputs first. Y, a vector with the dependent variable. So that now needs to be a variable which you have previously defined. That will be our my underscore Y. Okay, so this one will be my underscore Y. Explanatory variables, that's the second input. That's going to be the my underscore X. And you can read here output, that should be a 1 if you want the printed output a 0 otherwise, so we'll just put in a 1. And these are all outputs. You can leave the names as they are, but you could also give them different names. I'll just say this is my B. I'll just precede all of these with a my. But you can leave it as they are as well. So I'll put a semicolon here. Now I run the code. F5 to run the code, and everything works out fine. So here you can see the regression output. Down here that looks very similar to very standard regression output from any sort of software. and we can see two estimated parameters. Why two? We only handed in one explanatory variable. So if we go back to when we asked for help OLS, it says the function will automatically add a constant if the first column is not a vector of 1. So that's fine. So it has added a constant. This is what we usually want anyway. And we can see in R squared basically 0. Now it's not a surprise because both dependent and explanatory variables were random variables, so there's no way that our explanatory variable my x should explain any variation of my y, and we can see that in the R squared. And we can also see that the explanatory variable, the coefficient to the explanatory variable, which is the second coefficient, that this is not significantly different from 0, exactly as we expect. So we could run the code again. Just if you type into the command window CLC, that will, and press enter, that will clear the command window. So actually what I do quite often is I add this CLC command to the beginning of my script, because then whenever you run the code it will clear everything out of the command window. So let's run it again. Now you will see the results will be different. Why are they different? Because we've generated new random numbers. Okay, we generated new random numbers. Every time you run the code, the random numbers will produce new numbers, and therefore the regression result is going to be different. So if you keep on pressing F5, you will always get new results. Okay, but you'll always see that the significance of the explanatory variable is usually not significant. Let's go back and run a few more. P-value of 30%, 53%, and so forth. Okay, now there's one significant one at 5%. Now remember, when we're performing hypothesis tests, you expect to actually reject a correct null hypothesis a number of times, i.e. alpha times or alpha percent. I'm not going to explain this here, but that should ring a bell. If not, you have to go back to your course on what you did on hypothesis testing. We'll do some in econometric methods as well, but we assume you know hypothesis testing and you should revise what a type 1 error is and what not. Anyway, this is all I want to show, is how to run a regression with using the OLS est function. That's it.